All right, Algebra Lecture 10, and what we are studying is group theory. And it's important to have a nice collection of groups at our disposal. And we've already seen several examples of groups. And let's find some more. So one very important example of a group is a permutation group. And the permutation of a finite set, let's say we just take the set of the first n integers. For this, say x, is a function, say sigma, from x to x, that is 1 to 1 and onto. So for example, if n is equal to 1, we just have a set containing the number 1. And the only function from 1 to 1 is sigma of 1 equal 1. So that's pretty trivial. There's not much you can do with a function on a set with just one element to itself. What about n equal 2? So there are two functions, sigma, from this set to itself. So one of them is the identity function, let's say e, where e of 1 equals 1 and e of 2 equals 2. And the other is the transposition. That's what it's called, where sigma of 1 is 2 and sigma of 2 is equal to 1. So this just flips 1 and 2 around. And one way to write or describe a permutation is, for example, the permutation E. Let me write a matrix with 2 rows, 1 and 2. Those are the elements of the set. And the identity sends 1 to 1 and 2 to 2. On the other hand, if you take the transposition sigma, sigma sends 1 to 2 and 2 to 1. So this is a standard way of writing a permutation. It gets more interesting when you go to n equal 3. So n equal 3, let's say we want to find all permutations of the set 1, 2, 3. So what are the different possibilities? Of course, you always have the identity. So I'm going to use this 2-row matrix notation. For the identity, 1 goes to 1, 2 goes to 2, and 3 goes to 3. Another possibility, I'll call it tau sub 1. This is the transposition where 1 goes to 1, but 2 and 3 are transposed. So 2 goes to 3 and 3 goes to 2. You can also have the transposition where 2 is sent to 2, but 1 and 3 are interchanged. So 1 goes to 3, 3 goes to 1, 2 goes to 2. And tau 3 would be the transposition where 3, it doesn't move, 3 goes to 3, but the transposition interchanges 1 and 2, so 1 goes to 2 and 2 goes to 1. So here we have 4 permutations. This is the identity. Each of these fixes one element, but of course you can also have a permutation where no element is fixed. You can look at this as a picture. Suppose you have 1, 2, and 3, you can take the transposition that sends 1 to 2, 2 to 3, and 3 back to 1. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. And you could also have the cycle that goes in the opposite order. Instead of 1 going to 2, 1 goes to 3, 3 goes to 2, and 2 goes back to 1. So then we call that sigma inverse. So 1 goes to 3, 2 goes to 1, and 3 goes to 2. So here we have 6 permutations of 1, 2, and 3. And we need to ask, are there any more? Are there more than 6? And you have to think hard about this for a little bit. And then you can say to yourself, well, 1 has to get to something. I can choose any of 3 places to send 1 to. And then 2 can't go to the same place that 1 went to, because a permutation is 1 to 1. So you have 2 choices for where you can send 2. And once you've picked where 1 and 2 goes, there's only 1 guy left, and that's where 3 has to go. So the total number of permutations of 1, 2, and 3 is 6. You have 3 choices for 1, then 2 choices for 2, and then absolutely no choice for 3. It's fixed. And that S3 denote, this is the name, the group of permutations, well, in general, for any n. So I don't have to restrict this to 3. So S of n is the group of permutations of the set 1, 2, 3 up to n. So for example, S3 consists of these 6 permutations: E, the identity, the 3 transpositions, and these 2 cycles, sigma and sigma inverse. And what is called the order of a group G, which is denoted by G with absolute value signs around it, is the number of elements in G. So for example, the order of the symmetric group S3 is 6. 1, 2, 3, 4, 5, 6. There's 6 elements in it. Okay. Any questions about this? These permutations are really very, very, very important in group theory. And the name for Sn, where the letter S comes from, is called Sn is called the symmetric group. Now, whenever you have a function from a set to itself, you can always, if you have 2 such functions, you can always compose it. And that operation of composition is associative. So recall, this is from Calculus 1. Composition of functions is always associative. So this implies that composition is a is an associative binary operation in Sn, in the symmetric group. And the identity is just the identity permutation. And if a function is one-to-one and onto, it has an inverse. The inverse of a permutation, sigma, is a permutation sigma inverse, such that sigma composed with sigma inverse and sigma inverse composed with sigma. These are the identity. And we saw that every one-to-one and onto function has an inverse function. So Sn is a group. So let's look at an example. In S3, I have the permutation sigma that sends 1 to 2, 2 to 3, and 3 to 1. And I had another permutation I called sigma inverse that sends 1 to 3, 2 to 1, and 3 to 2. And the reason I can call this sigma inverse is, let's look at this under composition of functions. Sigma inverse composed with sigma. So if you look at 1, sigma sends 1 to 2. And if you apply sigma inverse to 2, it's back to 1. Sigma sends 2 to 3, and sigma inverse sends 3 back to 2. And sigma sends 3 to 1, and sigma inverse sends 1 to 3. So sigma inverse sigma is the identity. And if you look at this in the opposite order, sigma composed with sigma inverse sends 1 to 3, and then sigma of 3 is 1. So 1 ends up at 1. Sigma inverse sends 2 to 1, and sigma sends 1 to 2. So 2 goes to 2. Sigma inverse sends 3 to 2, and sigma sends 2 to 3. So again, sigma inverse composed with sigma inverse sends every number to itself. So this is the identity. Any questions about this? You really have to spend a lot of time working with permutations to try to understand them. Yeah, let's look at one of our transpositions in S3. Suppose I took tau, suppose I take tau 1, which is the permutation that interchanges 2 and 3. 2 goes to 3, 3 goes to 2, and 1 goes to itself. I claim the inverse of tau 1 is just tau 1. So let's see. Let's look at tau 1 inverse composed with tau 1. So tau 1 sends 1 to 1. And if you apply tau 1 again, so I'm looking at tau 1 composed with tau 1, sends 1 to 1. What about 2? Tau 1 sends 2 to 3, and tau 1 then sends 3 back to 2. Tau 1 sends 3 to 2, and tau 1 sends 2 back to 3. So every number ends up where it was. So tau 1 inverse is tau 1, or another way of saying that is that tau 1 inverse is tau 1 times tau 1, which is just tau 1 squared. And that's the identity. Any questions about this? I spent some time with sigma 3 because it's a very important group. It only has 6 elements, but it has lots of nice properties. Let's try to work out the multiplication table. For the group S3. So I have 6 elements, E, sigma, sigma inverse, tau 1, tau 2, tau 3, E, sigma, sigma inverse, tau 1, tau 2, tau 3. And the multiplication table means write down all the products. This times this. This times this. Now, E times the identity is the identity. In fact, E times any element of the group is the element of the group. So E times sigma is sigma. E sigma inverse is sigma inverse. E tau 1 is tau 1. E tau 2 is tau 2. And E tau 3 is tau 3. And similarly like this, if I take sigma times E is sigma, sigma inverse E is sigma, and tau 1, tau 2, tau 3, if you multiply by the identity, they don't change. Okay. So this is a 6 by 6 table. So the 36 multiplications we have to work out. And let's try and do it. We have to do a lot of group theoretic calculations. What is sigma times sigma? So sigma is 1, 2, 3 goes to 2, 3, 1. 1, 2, 3 goes to 2, 3, 1. What is that? So sigma sends 1 to 2, and then another sigma sends 2 to 3. Sigma sends 2 to 3, and then apply it again, 3 goes to 1. Sigma sends 3 to 1, and then sigma sends 1 to 2. So sigma times sigma is this permutation, which is exactly sigma inverse. So sigma times sigma is sigma inverse. Sigma times sigma inverse, we already saw, is the identity. And in the same way, sigma inverse times sigma is the identity. Let's see what goes here. Sigma inverse times sigma inverse. Let's figure out what that is. So sigma inverse is 3, 1, 2. So when we compose sigma inverse with itself, 1 goes to 3 and 3 goes to 2. 2 goes to 1 and 1 goes to 3. 3 goes to 2 and 2 goes to 1. But this is exactly sigma. So sigma inverse times sigma inverse is sigma. We also saw that tau 1 squared, tau 2 squared, and tau 3 squared, these are all the identity. So if you go down this main diagonal, you get E, 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 like this. This is tau 1 times tau 1, tau 2 times tau 2. But we still have to fill in all this other stuff. This is sigma tau 1. What is sigma times tau 1? So tau 1 fixes 1 and interchanges 2 and 3. Sigma sends 1, 2, 3 to 2, 3, 1. When I compose them, what do I get? 1 goes to 1, goes to 2. 2 goes to 3, 3 goes to 1. 3 goes to 2, 2 goes to 3. Aha. So when I compose sigma tau 1, I get this permutation which fixes tau 3, but interchanges tau 1 and tau 2. That's what I call tau 3. So sigma tau 1 is tau 3. What about here, this position? This is tau 1 times sigma. So tau 1 fixes 1, interchanges 3 and 2. Sigma sends 1 to 2, 2 to 3, 3 to 1. What do we get? So again, you have to keep in mind, this is really very important. It takes a while to understand. This is composition of functions. 1 goes to 2, 2 goes to 3. 2 goes to 3, 3 goes back to 2. 2 goes to 3, 3 goes to 2. 3 goes to 1, 1 goes to 1, so 3 goes to 1. So if I look at tau 1 sigma, I get this permutation. 2 goes to 2, that's fixed, but 1 and 3 are interchanged. So this is the transposition tau 2. So tau 1 sigma is tau 2. And what we see here is a very important fact. Sigma tau 1 was equal to tau 3. Tau 3 is not the same as tau 2, but tau 2 is tau 1 sigma. So the order in which I multiply permutations matters. Sigma tau 1 is not tau 1 sigma. So S3 is not an abelian or commutative group.
Sorry, Professor, probably a simple question. When you're doing that multiplication table, do you start from the row or the column to designate which is going first then? Does that make sense?
It's not a question of row or column. It's composition of functions. So for example, sigma tau 1, that's composition of functions. So just like in calculus, sigma tau 1 of x is you compute tau 1 of x, and then you take sigma of that. So sigma tau 1 of x is sigma of tau 1 of x. Right? This is composition of functions. So for example, sigma tau 1 applied to 1, that means sigma, let's say applied to 2 to make it more interesting. So sigma tau 1 of 2 is sigma of tau 1 of 2. Tau 1 of 2, so tau 1 fixes 1, interchanges 2 and 3. So tau 1 of 2 is 3. So this is sigma of 3. Sigma of 3 is 1. So sigma tau 1, sorry, applied to 2 gives me 1. Sigma tau 1 sends 2 to 1. So you really need to do a lot of calculations with pen and pencil and paper to begin to understand the operations of permutations. I mean, really, if you don't spend a couple of hours just studying permutations, calculating permutations, you'll never figure out what's going on. So S3 is important, and it's the first example, or the smallest example, of a non-abelian or non-commutative group. And maybe I'll leave it to you to fill in the rest of this table. Let me just do one more for fun. Suppose I want to calculate tau 1 times tau 2. So in S3, the symmetric group on 3 letters, as we say, tau 1, tau 2. This is the product of 2 transpositions. Tau 1 fixes 1 and interchanges 2 and 3. Tau 2 fixes 2 and interchanges 3 and 1. So when we follow this through. It's not matrix multiplication. Don't confuse it with that. It's just a matrix format, but there's no matrix multiplication here. Tau 1, tau 2. So tau 2 sends 1 to 3, and tau 1 sends 3 to 2. Tau 2 sends 2 to 2, and tau 1 sends 2 to 3. Tau 1 sends 3 to 1, and tau 1 sends 1 to 1. So this permutation, tau 1, tau 2, sends 1 to 2, 2 to 3, and 3 to 1. That's exactly sigma. So if I go back to my table, if I want to fill in tau 1 times tau 2, that's sigma.
Professor,
Yeah.
why are we starting at tau 2 instead of tau 1?
I mean, when I did this multiplication?
Yes, why you start at tau 2 instead of tau 1? Why we do?
Because this is composition of functions. Tau 1, tau 2 applied to x. This means it's just like in calculus. This is tau 1 of tau 2 of x. So I take x, first I calculate tau 2 of x, I get a number y, and then I compute tau 1 of that y. It's just like calculus. If you had, in calculus, if you have the functions f of x equals, I don't know, cosine x, and g of x is x squared plus 1, f composed with g of x, that's f of g of x, that's the cosine of x squared plus 1. But g composed with f of x, that's g of f of x, that's g of cosine of x, that's the cosine of x squared plus 1. And these two things are completely different. It's just like composition of functions from calculus.
Okay. Thank you.
What's another example of a group? There's something called the circle group. So if you look at, this is a set of all complex numbers of absolute value 1. This means all numbers x plus yi, where x squared plus y squared equals 1. And in the plane, x squared plus y squared equals 1. That's just the circle of radius 1. You interpret a point in the plane, xy is x plus yi. This is I. This is minus I. Just the circle. And you know that if w and z are complex numbers, then the absolute value of w times z is the absolute value of w times the absolute value of z. And again, the circle group is all complex numbers of absolute value 1. All complex numbers z, the complex numbers, absolute value of z is 1. If w and z both have absolute value 1, so does their product. If 1 times 1 is 1. So this set of complex numbers is closed under multiplication. And if z is x plus yi, and absolute value of z is 1, then z inverse is x minus yi, sometimes called the complex conjugate. And the product of these two is 1. So this set of complex numbers with absolute value 1 is another example of the group. It's an infinite group because circle has infinitely many points on it, and it's abelian because you multiply two complex numbers, W and Z, it doesn't matter whether you write ZW or WZ, you always get the same thing. Now, if this is the first sort of advanced class in mathematics that you've taken, where you're no longer just differentiating and integrating functions or doing things which are kind of mechanical. This is a course where you have to learn what is a mathematical proof and how to prove things. We spend almost all of our time proving results about groups. And I'm about to prove one of the most important results, which is called Midrange's theorem. And it has to do with the subgroup of the group. So let G be a group. A subset H of G is a subgroup of G. This is the definition. If it satisfies the following properties, first of all, H isn't empty. H has something in it. H is non-empty. It's closed under multiplication, so if A, B are in G, or in H, then A times B is in H. And it contains the inverse of each of its elements. If A is in H, then A inverse is in H. And notice, so this is the definition. Let's see. What's an example? Well, here's an easy example. Suppose we let G equal Z, which is the additive group of integers. Let H equal 2Z, which is the even numbers. 0, plus or minus 2, plus or minus 4, plus or minus 6, and so forth. So this is not empty. Here the group is addition, not the group operation is addition, not multiplication. And if you add two even integers, you get another even integer. And the inverse of an integer, n, is minus n, and if n is even, so is negative n. So this is an example of a subgroup. And in fact, for every integer m, by that h be mz, this is a set of all multiples of m, 0, plus or minus m, plus or minus 2m, plus or minus 3m, and so forth. This is closed under addition. It's the sum of two multiples of m is another multiple of m. And the inverse, you have a multiple of m, it's negative, is another multiple of m. So this is another subgroup of the integers. And if you take the special case where m is equal to 0, That's the set of all multiples of 0. That's just the number 0 all by itself. That's a subgroup. And if you take m equal 1, then h, which is 1 times z, just all multiples of 1, that's all integers. So these are kind of the trivial examples of a subgroup of G. And this example works for any group. In every group G, the set consisting just of the identity and G itself are subgroups of G. So every group, if it has more than one element, always has at least 2 subgroups, namely itself and the identity. And this is just standard terminology in mathematics, so it's good to hear it. So the set consisting of just the identity is called the trivial subgroup of G. And H is a proper subgroup of G if H is not all of G. It's words that people use all the time. Any questions about that? So let's prove some properties of groups. These are little theorems. The first is in Article 35 alpha. It's actually said there is a homework problem, but I'm going to do it. It says that a non-empty subset H of a group G is a subgroup of G if and only if A times B inverse is in H for all A and B in H. And the proof, well, if and only if means you have to prove this, that the left side implies the right and the right implies the left. So let's prove it first going from left to right. So suppose H is a non-empty subset of G, and A and B are in H. So if B is a subgroup, if B is in H, then B inverse is in H. Because one of the conditions for a subgroup is that it contain the inverse of each of its elements. And then A and B inverse both in H. H is closed under multiplication, so A, B inverse is in H. So that proves that if H is a subgroup, then it satisfies this condition. So the more interesting thing is to prove that if this condition is satisfied, then H is a subgroup. So I want to go now from right back to left. So H is non-empty. So that means that there exists an element A in H. Which means I can take A and B equal, which means that A inverse is an H. Because if A and B are an H, so is AB inverse, A times B inverse. This doesn't say A and B have to be different for any A and any B. So take B equal to A times A inverse in H, but A times A inverse is the identity. So the identity element is in the subgroup. So let B be an H, then E B inverse is an H, but the identity, because E is an H and B is an H and E B inverse is an H, so B inverse is an H. So if an element is an H, so is its inverse. And so then I have to, so H is closed under the operation of taking inverses. And finally, I have to show that H is closed under multiplication. So let AB be an H. Then we know, we just proved that B inverse is an H. And if A is an H and B inverse is an H, then A times B inverse is an H. But if you take the inverse of an element and then the inverse of that, you get back to where you started. So B inverse is B, so AB is an H. So this is the proof. And again, when you, in a proof like this, every word, every symbol, every mark on the paper is important. And you have to understand in great detail exactly what is going on. Right? Questions about this? Okay. Let's prove another theorem. This is the assertion in 35 beta. It says that H1, H2, up to Hn be subgroups of a group G. Then if I take the intersection of all of these subgroups, we call that H. This is a subgroup. G. So we want to prove that the intersection of subgroups is a subgroup. So first of all, if H sub k is a subgroup of G, that means the identity element is in HK, and this is true for all K. Which means if I take the intersection of all of these subgroups, which is this set H, E is in every one of the sets, so E is contained in the intersection. So this set H is non-empty. H is a non-empty set. That was the first condition for being a subgroup. Subgroup can't be empty. It has to have something in it. Now, what else can we say? If an element B is in H, that means B is in the subgroup HK for all K from 1 up to N. But a subgroup contains the inverse of each of its elements. So B inverse is also in HK for all K, which means B inverse is in the intersection of all the HKs, which is H. So if B is in H, B inverse is in H. So H is closed under the operation of taking inverses. Finally, we have to show that H is closed under multiplication. So if two elements A and B are in H, that means A and B are in every one of the HKs, which means A and B is in the subgroup HK, A times B is in HK for all K. Which means AB is in the intersection of all of these subgroups HK, which is H. So this means that H is closed under the group multiplication. I have a subgroup, so that completes the proof. So you need to take some time to study these, because these are all standard methods of reasoning in algebra. This is what you have to learn. Okay. Any questions? Okay, well, let's keep on proving stuff. So there's an operation in group theory called conjugation. So if A is in the group and X is in the group, then we can write down the element AX A inverse. This is called conjugation of X by A. So if you conjugate X by A, that means taking the element AX A inverse. And so this is our next little theorem. So this is 35 gamma. That H be a subgroup of the group G, let A be in the group, and then we look at what we get. But if we conjugate all elements of H by A, so we look at all elements of the form AX A inverse, Well, the book does it slightly differently, so let me follow the notation of the book, though it's essentially the same thing. So let H superscript A be all elements X in G such that AX A inverse is in H. So we look at all elements X in G, where AX A inverse is in H. Then HA is a subgroup. That's what we need to prove. So you have a subgroup H, and you look at all elements such that AX A inverse is in H. So how can we prove this? So first of all, if I take X equal to E, AE A inverse, this is the identity. AE is just A, so this is A inverse, this is E. And E is certainly in H because every subgroup contains the identity. So the element E satisfies this condition. AE A inverse is in H. So A is in A sub H. And we have to show that A is closed under multiplication. So suppose X and Y are elements of A sub A. So this means that AX A inverse is in H, and AY A inverse is in H. But H is closed under multiplication. So AX A inverse times AY A inverse is in H. But what is this? This is AX A inverse A. So this is my AX A inverse times AY A inverse. A times A inverse is the identity. This is just A, these cancel. This is A, XY, A inverse. So A, XY, A inverse is in H. So that means XY is in HA. So HA is closed under multiplication. And finally, if X is in HA, that means AX A inverse is in H. H is closed under taking inverses. So AX A inverse inverse, what is that? That's exactly AX inverse A is in H. Which means X inverse is in HA. So this set HA is closed under the group operation, multiplication, and inverses. So it's a subgroup. Questions? So what's really very interesting is when you have a group, you can look for all of the various subgroups of the group, and they often tend to be quite interesting all by themselves. So here's another example. Remember that A group G is abelian or commutative if AB equals BA for all A and B in the group. But not all groups are abelian, and we saw that S3 is a non-abelian group. So let G be a group what is called the center of G is the set Z sub G, which is all elements in the group which commute with every element of the group, such that AX, XA equals AX for all A in the group. So not all pairs of elements in the group commute, but you might have some elements X, which then just that element X commutes with everything. XA equals AX for all A in the group. And the theorem, which is 35 delta, says ZG is a subgroup. Of G. Now, first of all, if you take the identity, EA equals AE for all elements A in the group, this is the identity. EA and AA are all equal to A. So E is in the center. So the center is non-empty. All right, next. If X and Y are two different elements in the group, then for every A in the group, we have the following. XY times A, by associativity, this is X times YA. But Y is in the center. So YA is the same as AY. And again, by associativity, X times AY is XA times Y. And because X is in the center, XA is AX. And again, by associativity, AX times Y is A times XY. So XY times A is A times XY for all A in the group. So X times Y is in the center. So the center is closed under multiplication. And finally, let X be in the center and A be any element of the group. We know that AX equals XA because X is in the center. So if two elements are equal, their inverses are equal. If the inverse of AX is X inverse A inverse, and the inverse of XA is A inverse X inverse. So for every A in the group, X inverse A inverse equals A inverse X inverse. So if you take any elements in the group and it's the inverse of something, X inverse commutes with everything. So X inverse is in the center. And that's the proof. I could have written, if I wanted to write this in just one line, A inverse X equals XA inverse. Take A in the group, A inverse is in the group, this relation holds. So the inverse of this equals the inverse of this. This is equal to x inverse A, and this is equal to AX inverse. And then that's a direct, maybe a more direct argument, but it's the same argument. Let me prove one last result, and then I think we'll stop for the morning, because these are a lot of theorems to have to work through and try to understand. So this is the final result, which is, the author calls this a proposition. 35, it says, if H is a finite subset of a group G, and whenever A and B are two elements of H, then AB is an H, then H is a subgroup. Should add, this is a non-empty finite subset. So remember, what are the two conditions for a subset of a non-empty subset of a group to be a subgroup? It's closed under multiplication and it's closed under taking inverses. So we're assuming that this set H is closed under multiplication. So what we have to do is show, so must show that if A is an H, then A inverse is an H. So notice, if A is an H, then A times A, which is A squared, is an H, because H is closed under multiplication, which means A squared times A, which is A cubed, is an H. And if you continue inductively, you get A to the n is an H for all positive integers n. But this is the important point. H is finite. So this set of powers of A is a finite set, because it's contained in H, which means they can't all be different. So therefore, there exist integers m less than n such that A to the m equals A to the n. And A to the m is an element of G, so A to the minus m is in G. So if I multiply this on the right by A to the minus m, since if A to the m equals A to the n, then multiplying by A to the minus m, still an equation. This is A to the m times A to the minus m. This is the identity. And this is A to the n minus m. And n minus m is at least 1. Let me just call this something. I'll call this P. So we get A to the P equals 1, which means that, oops, A times A to the P minus 1 equals the identity. So A inverse is a to the p minus 1, because if you multiply this by a, you get the identity. So this is in this set. So let me repeat this argument because it's a very subtle argument, perhaps. H is a non-empty finite subset of a group that's closed under multiplication. And I have to show that it's closed under inverses. So if I take any element A in the set H, I have to show its inverses in H. But because H is closed under multiplication, if A is in H, so is A times A, which is A squared. And then A squared times A is A cubed. And A cubed times A is an A to the 4th. By induction, you get every positive power of A is in H. But this looks like an infinite set contained in H, but H is finite. So these elements can't be the same. You have to have two different numbers, m less than n, where a to the m equals a to the n. So if you multiply by a to the minus m, you get a to the n minus m is the identity. N minus m is some positive integer, I'll call it p. So a to the p is the identity. If p is 1, that just says a is the identity. That's not so exciting. But otherwise, p is bigger than 1, and a times a to the p minus 1 is the identity. So this element has to be the inverse of a. So the inverse of a is an h. And that's the proof. Okay. Any questions about this? All right. So we just went through a nice chunk of group theory. And really everything I did today, all of these kinds of proofs are fundamental things. So you have to understand these proofs, and on an exam, I will definitely ask you to prove things. And what you have to know are the techniques of proving theorems in algebra. And the ideas that come up in these proofs, these are the ones that you need to know. Any questions about this? Okay. If not, then we will quit for the day. It's supposed to be a beautiful day today, nice and warm, so everyone enjoy themselves if you can. And I have office hours today. I have 2 different office hours tomorrow, in fact. So I encourage you to log on and ask questions if you have some questions. Okay. I just saw there was a question in the chat from 25 minutes ago. So if you have a question, do not put it in the chat. Just unmute yourself and ask your question. Otherwise, I won't notice it. Okay. All right, all. Next lecture is on Wednesday. Bye.
Thank you.